thanks a lot for the kind introduction. I hope you can hear me, and even if I go away a bit further like this, it still works. Okay, let's see. So, first of all, I'm glad that many of you have stayed here. Apparently, there's some interest in conducting a course on terrain analysis. In fact, this is the third course in that similar setup, I would say, here at the IIT Roorkee. We have, the first course I think that we gave was very introductory, giving an introduction to TopoToolbox and just some basic stuff. The second one was a bit more complicated, looking at a landslide susceptibility analysis that we then together conducted here using some specific tools in TopoToolbox. And well, what I want to do, or we want to do today and tomorrow, is looking at ways how we can employ TopoToolbox to analyze long-term erosion rates. Okay, so the plan is we have quite some time together. So we would have 1.5 hours today. And tomorrow we actually have 3.5 hours. So I think we can use that time also. But what we want to do today is that we just give a brief introduction. We see whether all the technical setup basically works. I give a brief introduction also to TopoToolbox. So that's the plan. And then tomorrow we would then start full force. Okay, but just a little bit of background. Now, when we say we will analyze long-term erosion rates, well, what means long-term actually? Okay, so you all know the term of erosion, which is the removal of material from the Earth's surface by flowing water, by the wind, by the glaciers. So a geomorphic process that acts on the Earth's surface and can create landforms like this one here. This is a gully system somewhere, not in India, I guess, no, in Australia. But it shows something that causes a severe problem, soil erosion, which just destroys arable land. This is not what we are going to do here in this course, okay? This is a bit on very short time scales of tens or years to tens of years, okay? Okay, so, well, erosion also happens, of course, on very, very long time scales. Like when we look at the belts, like here, a view across the Himalaya, looking over the, I think it's Arun catchment towards the west. Of course, here, erosion also plays a big role in denudation of the major Earth landforms, big mountain belts. Also, this is not what we are actually going to do. But we will be somewhere in between on time scales, let's say. So when I'm talking about long time scales, on age or over years or time spans of 1,000 to perhaps 100,000 of years. I mean, that's also a very long time scale. And those that are working, let's say, on meteorology, amongst those here, this might be a very, very long time scale. Still, a lot of the techniques that you will learn as part of this course can obviously also apply to shorter time scales. So what we will use as part of this course is so-called 10 beryllium derived denudation rates. So this is a method used mainly in tectonic geomorphology, which is based on the fact that in our Earth's surface, you have an accumulation of different isotopes. These isotopes are produced either in situ or by atmospheric production and stem from some interactions in the higher atmosphere, spallation processes, which lead to an enrichment of these, for example, 10 beryllium in the upper Earth surface. I won't go into much detail about this technique. Dozens of papers that would do it better than I can do. What the specialty about this approach is that you measure it relatively easily, okay? Or the measurement, let's say the lab stuff is not that easy, but basically what you can do, you go to the field, you go, for example, to a river with a more or less well or big catchment size, let's say something more than 5 square kilometers, and sample sand. Okay, so you take about 1 kilo of sand, and the idea is that this sand comes more or less from the entire catchment, and that nature does the averaging. So it takes all, or you have sand from everywhere, it's going to be mixed within the river by its turbulence and by sediment transport, and will be deposited at some point somewhere on some point bar, for example, and that's where you are, and you are going to sample that sand and bring it to the lab. And then a lot of work starts. You would try to extract the sand by physical methods, by chemical methods, or not the sand, but the quartz, and then you would try to extract the 10 beryllium from that quartz, and that is something that you would measure with a AMS spectrometer. So that's where this stuff becomes expensive, because that is a measuring device that usually you don't have at your institute, but there are some special institutes that provide that service. In Germany, I would say measuring one such sample costs about 200 to 250 euros. Okay, so that's the really expensive part. So the good thing is that you don't necessarily need to do that by yourself, but that existing data exists. So, for example, the Octopus database provides easy-to-use interface to basically all the samples that were taken and processed worldwide. These samples were then processed or post-processed by a common method. So they are intercomparable. The Kern method, which does everything which is required to calculate from the 10 beryllium concentrations the erosion rates. Okay, as I said before, this is just to give you a short understanding of what kind of data we actually deal with. You can get that data here. So this is octopusdata.org. It has been developed by the University of Wollongong in Australia. And it's maintained by them as well. And there's always new data coming. And you can see that quite some data exists for an area that we might be interested in, the Himalaya. Okay? And so the idea in our course is to try to answer following research question. Okay? Saying what controls basin-wide denudation or erosion rates in the Nepal Himalayas. So we will work with data from Nepal and trying to find out how can we actually model that. So when I talk about denudation and erosion, does anyone know what the difference is? There is at least a difference in the German terminology. Denudation is more like the aerial wide lowering of the land surface, while erosion is more the incision and fluvial erosion. So basically what we are looking at is denudation, the lowering of the entire landscape rather than the incision. And that happens over time scales of, let's say, a rate of a couple of thousands of years. Okay, so the outline that we are going to follow is, or what we want to do is, first of all, get started with MATLAB and TopoToolbox. Okay, so I will explain a little bit about how TopoToolbox is structured, and I give a brief introduction into some main numeric classes. And then we will learn about the data and how to read it into MATLAB, reading shapefiles, and also downloading DEMs, so digital elevation models. We will learn how to calculate some basic topographic attributes like flow directions and delineate stream networks. Then combining both data, so the basin-wide denudation rates and our digital elevation model and all the derivatives that we have, they somehow need to combine, and this brings a couple of challenges with it. So we try to deal with georeferencing uncertainties and learn about some special approaches here that a seemingly simple tool, Snap-to-Stream, basically offers. We will learn about summary statistics, and then going actually a bit beyond that, we will talk about statistical modeling of erosion rates. And that means, in that case, a bit of nonlinear model fitting, or let's see what works best, or quantile regression. Okay, so that's kind of the outline that I would like to do with you. And so let's see how that works. But before we actually start, we need to set up our system, okay? And to do that, and to also get an idea about what you bring as a pre-knowledge or pre-existing knowledge, I would like to ask you to also connect to this other pad here. So YoPad, so if you scan this QR code, this will automatically bring you to that pad, okay? Alternatively, just use your laptop and enter this URL to open that Etherpad. So what is this Etherpad? Well, it's just a common editor where we can all write into, okay? And I have it open here, okay? So I think if you open that one as well, you can basically also start writing into this. Yes, it works. Okay, so anyone or everyone connected? So just to get a brief idea about what you know about, let's say, or about your background, here are a couple of questions. So for question 1 to 3, please just use a vertical line, so like this symbol here, just a vertical line, behind these double quotes to choose where you would assess your level of expertise in geographic information systems. Probably, I'm pretty sure that the system itself will have problems here, because so many people editing one manuscript at the time is, of course, even here a bit challenging. That's kind of a funny way to create a histogram. So I see as a polling tool, it doesn't work so well. But it was worth a try, I guess. But, I mean, let's see. Over time, it will hopefully come to an equilibrium. What you can also do is, what do you expect from this course? So if you like, you can, of course, also write that in your own editor and then just copy and paste it here. Here you can just use a open text. Okay, conquer the MATLAB, okay. Learn better histograms, yes. Refresh MATLAB skills, okay. Okay, obviously the system is a bit overstrained from many users, but I think it should work better if you write your text, at least for the last one, just as a plain text somewhere in your editor and then copy and paste it. That would probably be easier. Gulab, okay. Okay, so we will use that tool anyway. It doesn't work when we use it all together, obviously. From what I've taken now, basically everything is deleted. And I'm not much more smarter than before about what you actually bring here as an expertise. But what I've seen is that the level of expertise in geographic information systems was like intermediate, it seemed like, okay? Yes? Okay, now it disappeared. Okay, who is doing that? Because actually it's not a, Now I have to ask it again, and please just raise your hands. Who has worked on terrain analysis before? Okay, a few hands up. That's good. For the others, if you haven't worked with digital elevation models before, what could you use it for in your own work? I mean, if you just want to say, perhaps we can also have a mic being passed around, and you can just briefly say what you would need digital terrain analysis for, And perhaps by that we can also learn about what you would expect from that course. Does anyone want to say something here? Come on, this is supposed to be interactive.
Maybe terrain analysis can be done so that we can have a better indentation area, like when we do for flooding and all, like to better capture where is it is happening and all.
So for delineation of flooding areas, or?
Like if you don't have the proper elevations and all on further studies, we may not be able to capture what is happening in the area better, is I presume.
Yeah. So you mean the area? I didn't get that entirely. Like the area of the samples? What do you mean?
Like I think the question you are asked is like how this elevation will be useful for your study, right?
Exactly.
So, like usually in studies, we require the elevation in order to know like which area will be flooded. Let's say for a flood case study, which area will be flooded more, or will it be like in a safer zone kind of thing? Or maybe in the case of an erosion study, also we require the different elevation areas to know like the different erosion rates and all.
Yeah. Exactly. So, but you're totally right. Probably a lot of amongst you are working on hydrology, or who's working on hydrology? Okay, not so. Exactly. Yeah. But first of all, yes. So for flood inundation modeling, I mean, a DEM is just super mandatory. It just gives you the basic input into any hydrodynamic model. For erosion and sediment modeling, well, a simple approach is just to calculate steepness, or let's say the slope, which gives us a first order control basically on the amount of erosion that happens somewhere. Of course, it's a bit more complicated than that, but for most geomorphic analysis, such a DEM is also required. Anything else from the field of meteorology or so? Okay, so it's pretty much, as far as I understand, as what we are planning to do in that course. So looking at, let's say, sample locations, find out, well, what is the upstream area of these, or upslope area of these samples, so that we know over which areas those samples integrate, and then find some specific variables to be able perhaps to predict erosion rates from those that we have measured. Yes, there is another one. Sorry.
Sir, it's also used for making contour maps.
For making contour maps,
Yes,
yes.
sir.
Yeah.
Basic.
It's a very basic but common thing to do with elevation data. Okay, so to create just a map base for visualization. I think there was another raised hand behind.
Sir, how can this tool be used for urban floods?
For urban floods, yeah. Well, for urban floods, I guess you would also have, at best, a high-resolution DEM. In particular, if you want to represent individual houses or other structures. What is difficult here is that basically urban areas represent real 3D areas, and DEMs, so digital elevation models, are actually only 2.5D. So any underpasses or tunnels or whatever are actually not represented. This makes it a bit more difficult, but not impossible. TopoToolbox itself doesn't actually have a hydrodynamic model in that case. We are currently developing that. It's actually also nearly available, which just does a kind of steady state flooding. What TopoToolbox in that respect could be very helpful for is in pre-processing your data. So to make sure that you actually model pathways without the influence of structures and so forth.
Sir, one more question. Sorry. Basically, the open source DEM which we use is 30-meter resolution. So, how does that impact on the uncertainty of the model?
Okay, that's getting specific now. Well, if there, often you don't have any better model. That's of course the case. It means, of course, that you have a lot of, let's say, mixed pixels, so pixels that record different elevations in that case. You get a lot of artifacts, which might be difficult to correct for in the end. Whether it's always true that higher resolution results in higher accuracy, that might be true for urban flooding. In some other cases, you introduce a lot of variability also with the high resolution models, which you actually don't want. Sometimes that might be just too much. So for example, if you calculate sediment and flow paths across a landscape, if your DEM explicitly depicts, let's say, roads and stuff like this, then these can influence highly where water is basically routed. And then always keep in mind that you have a 2.5D representation of the surface and not a 3D representation. And so these flows and so forth might very much differ from reality. And then it's sometimes better to have a coarser model that doesn't have that variability.
Hi, sir. This tool, is it used in coastal erosion studies as well?
Not that I know of. So coastal erosion, I mean, I'm pretty sure that, what I will show you is TopoToolbox is a very versatile software which allows you to prototype your own tools, to develop your own approaches. It's not, it's a bit like a GIS in some respects, but it has some more capabilities. You could apply it, but there's not, for example, some wave modeling which would allow you, let's say, to model the erosion going on along coasts. Yeah.
Okay, sir. Thank you, sir.
So thanks a lot for the feedback. This is already good to know. So let's go back to our slides here. Next thing, what we want to do is to work with TopoToolbox. I'll explain later a bit more what that actually is and how it works. But what we need is MATLAB. And now I've heard that some of you don't have a license. I've actually passed some information to the organizers and hoping for that you would get this information. But that said, okay, you need MATLAB installed together with the image processing toolbox and the mapping toolbox. So at IIT Roorkee, as far as I know, you have a headcount license, which means you all have access to MATLAB, and I think many toolboxes. It's exactly the same like we have it at the University of Potsdam. So Potsdam students also have access. But for those coming from other universities or other places, you might not have the license. Is that right? Who doesn't have access to MATLAB? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, pardon? It might work. I'm not sure whether the trial version also offers you working with the toolboxes. Does that work? Okay, so we can try. Another option, so I was in contact with some representative from MathWorks India before, and I will try to get some license, but I doubt that I will get those until tomorrow. So perhaps if I know that some of the organizers, where are they, wanted to check out whether that would be possible, that even that you would somehow also be eligible for the IIT Roorkee. I know the licenses. I know it would be difficult in Potsdam, actually impossible. But perhaps IIT Roorkee can make things possible, I don't know. Okay, but now if you have that, and I hope that, who has MATLAB already installed? Okay, that's most of you. And if you have done that, well, first of all, where's my MATLAB? No MATLAB right now. So if you type VER, so I hope you can see that. It's just the command to list all the toolboxes that you have in your version. And so it should list at least the image processing toolbox and the mapping toolbox, okay? What is good to have is also the parallel computing toolbox and the optimization toolbox. So for those having MATLAB installed, if you type the var command, does it look like similar like here? Or are some toolboxes missing? Or, I mean, probably they're missing some, but hopefully you have, as I said before, the mapping toolbox, image processing toolbox, and yeah. I mean, no, statistical machine learning toolbox, we don't need it strictly, I guess. Okay? So if you have that, then, unless you haven't done that already, as a second step, you should download TopoToolbox, and you find it under that link. So it's currently hosted on GitHub. Let's just click that. This is how it basically looks. You'll see all the code here. You'll see then a description, a README file. And that's a bit difficult to find if you want to download it. There are different ways to do that. There are better ways to do that in MATLAB also because it allows for versioning. But the simplest way would just be to press here, download zip. Okay, so then it zips everything. You are asked to store that somewhere, and at best, I mean, you just place it somewhere on your hard drive under documents. I have an extra folder, MATLAB, and then in that MATLAB folder, you would just store that zip file and unzip it, okay? So that means once you have done that, TopoToolbox is in an extra folder somewhere on your hard drive. And the next thing you need to do is to tell MATLAB, hey, there is some code that you should be able to run if I want you to. Okay, and that requires that MATLAB knows where these tools are. And to tell that MATLAB, you would go on the home button here, or the home ribbon, and then say set path. Okay, so this dialog shows you all the folders in which MATLAB looks for files. Okay, and you see most of these files and folders are obviously in the installation of MATLAB. So and you can see there's some interface functions, some stuff that deals with different data types. I know, we don't need to bother. The important thing is that we now add the folder that we have. Let's say this one here. If your unzipped folder is just called toolbox, probably TopoToolbox in that case. So like here. And you would just say add to path with subfolders, and you would just add the entire folder. Okay? So once again, you go to GitHub, go on code, you download the zip to some location on your hard drive, at best somewhere on the documents or so. You unzip it, and then you add this folder to MATLAB's search path. So once you have done that, then you just press save. You might need admin privileges to make that really permanent. Otherwise, you would need to repeat that. Alternatively, instead of using that set path thing, you could also just say add path gen path. So generate a path with all the subfolders and add those paths. And you would enter the folder, or we can take like this one here. So like this. So the folder where you have placed all your files, you would add them to the system, to the MATLAB system, just in that way. So Jürgen is going around and checking whether that works or not. If you have any problems, I can't see those from up here, so let me know. Sometimes I don't know whether you are already bored and say, okay, hello, I'm already done since ages, or whether you panic and say, I have no clue. So just let me know. So you can check whether that works, okay? By typing following command. We'll learn more about it just in a second then, but SRTM, oops, like this. It's a bit long, I'm sorry. DEM equals a grid object, OBJ grid object. You need to use the capitals, right? And then it says it should read the SRTM Shuttle Radar Topography Mission DEM of the Big Tahunga 30-meter DEM. So that's just a file name here, which comes in as a UTM zone georeferencing, UTM zone 11. Okay, so that's somewhere in California. And if you then press enter, that should work. It should not return an error. If it returns an error, then you either didn't set the path right, or you didn't install MATLAB, or no, you probably had installed MATLAB so that this works, but it's there's some other issue. Zoom, a bit, yes, I can try that. Yep. So now it should be a bit bigger. Is that okay? Or should I increase it even more? More? You want more, okay. Like this. Is that okay? So perhaps while you're trying to fix any problems, if your desktop looks a bit different than mine, what it probably does, you can change the view. No, not here. No, you can change the layout, just the default layout. That's what I'm currently or usually use. And this GUI or IDE, Integrated Development Environment, is structured as follows. Here on the left-hand side, you have some a folder overview. The folder that you are in here, that's your working directory. You have a command window. We will usually need this one to just enter commands, but also it is good just to use the editor. Here you can write your own code and then store it and then also execute it. And finally, there's, or not finally, but there's a workspace which contains all the variables that you have created. And finally, you can also look at the command history. You can add that one. And so here you can scroll through your history and rerun code, copy, paste it. Okay. So may I ask, now for all of you, if you run that code, this one here, so with your arrows, you can go up and down in your code. Does that work? Okay. Does it work for everyone? Or does it not work? Okay. Okay, so here it's also explained again. Is anyone using a Mac? Okay, so it works. Excellent. So those of you who might have a new Mac with a relatively new operating system, there are some issues sometimes in running TopoToolbox. These issues are related to some compiled code, which you automatically get once you download the data. In that case, if you have a Mac and some newer operating system, it might be required to recompile some of that stuff using the compile max files. But that requires also you to have a compiler on a Mac. This is usually Xcode, I think. Okay, and finally, just a note of caution. Currently, we are a bit in a transition between two versions of TopoToolbox. So currently, we are developing TopoToolbox 3. which is under construction. It's a DFG, so German Research Foundation funded project. It's actually already accessible. You could also download that version, but I cannot guarantee, neither I can't for the other software, of course, that it's like bug-free. It's not yet fully tested, and some of the stuff is not fully ported yet, let's say. In the end, it doesn't matter that much. Most changes will not affect the existing syntax. So what you write in TopoToolbox 2 will also work probably in TopoToolbox 3. What you will gain with using the new version is increased speed, better handling of coordinate projections. Many tools might also work with geographic coordinates. So if your data comes with latitude and longitude rather than x and y as a coordinate system, and there will be a better help and documentation. It also means that, developing a new version was also necessary because TopoToolbox tends to, there are a lot of new developments in MATLAB, which we haven't followed that much. And now they tend to, usually MATLAB is backward compatible, but it now starts throwing warning messages. So if you have a very new version of MATLAB, like 2024, A or B, then you might get a warning message here and then. If you want to just get rid of these messages, just type in your command line warning off. Then you won't get any warnings. Now, perhaps as one teaser in relation to our project and TopoToolbox 3 project is that you can actually expect PyTopoToolbox in the future. So there will be a Python version. There will be an R version, TopoToolbox R. And both, actually, as well as the MATLAB version, will rely on libTopoToolbox. So currently, we have different strands of development. It's like leading a small software engineering team at the moment. So I have a research software engineer who basically develops a lot of the code that MATLAB provides in C or C++, so making it super fast and also callable or as bindings to other programming environments, and that's Python and R. Okay, so but that's still, I would say, a couple of months to go until those are really ready, and even then, they won't be as comprehensive as the MATLAB version. That will take some more time, and in particular, some community input. Yes, I've never tried that. So Octave is a MATLAB clone, let's say. It's free, and most basic commands would work in the Octave version as well. The problem is the toolboxes. So image processing toolbox, I think, should work as well. Mapping, I'm not sure. I think for the mapping toolbox to develop in Octave, there's probably not a big community to do that. Okay. So now it is, let's see, 5:30. How about you? Are you already very tired? No, we have some more time than tomorrow. If I just will talk about a few things about, you can expect here in that course and what kind of software you actually learn. Go through that relatively quickly, okay? But what I want to emphasize, first of all, is that, you have already mentioned a couple of these examples, but that terrain data gives us a lot of information in diverse geo-related disciplines, let's say. And this can be visualized or felt, basically, when looking at that image, which is an aerial image or a satellite image of an area in Oregon in the US. And you can see a road that runs through that landscape. You see a lot of forest, basically. Okay? But once you basically remove the forest and you unveil the topography behind using a LiDAR DEM, this one was enhanced a little bit by using hill shading and even a bit of coloring. You can see basically the processes that go on in that landscape. So here, no idea But here you can see something. What can you see here? So interbreeding hill shades is always the first step in terrain analysis, I would say. But what can you see here? Yes? Exactly. So you see, apparently it's these long tongues that start at this kind of edge, okay? And then go into a southwest direction and form these long tongues. And those are actually landslides, yes. So which have detached from that alluvial terrace up here. So apparently the river was perhaps a bit higher in ancient times. Whatever changed, perhaps climate changed, perhaps the base level of this river changed. It started to incise, it migrated left and right, formed a new valley, oversteepened the valley flanks, and these oversteepened valley flanks apparently have the tendency to fail. Okay, so they might produce some quite large landslides, and the picture is actually missing. These are very impressive, actually, in the on the photo that is not here, unfortunately, but which also created one of the deadliest landslides in the US, the Oso landslide, which is one of those. Okay, so you can even see, okay, these are landslides that traverse the river has incised back into those deposits, and so forth. Okay, so analyzing this data, that is the aim of TopoToolbox. So what is TopoToolbox? It's a library of functions for the analysis of digital elevation models. I usually say it's just a library, because what I want to emphasize with that is that it's a set of functions that you can assemble by yourself. Okay, so it's about being creative with that software and not just using predefined workflows, but developing your own workflows with that software product. Okay, so the development started pretty early, 2008. So I actually started my PhD with the software. At that time, I was not so familiar with software development, so it was very basic, let's say. But over the years, realizing that it's being used a lot, so there was definitely a need for such kind of software, we started to develop version 2 also that became more professional. Then starting also writing the TopoToolbox blog on topotoolboxwordpress.com. And then a lot of new stuff came, like TTLEM, a landscape evolution model, and then various new versions, not at a particularly high speed, right? So when you see how often other software gets updated, Adobe Illustrator or so, I mean, that's not comparable, of course, but we have a very slow path, okay, and pace, let's say. But it's growing, and so there were some new additions for the analysis of divides, point patterns on stream networks, another landscape evolution model. We have not just added, I mean, it's just working with TopoToolbox 3, graph flood, which is a hydrodynamic model. And then, as I said before, now we started the development of TopoToolbox 3. So the software is actually older than 15 years, which is quite old for a software, I would say. So usually I talk a bit more about the motivation behind. I think what is perhaps from my personal point of view was important as a student, and also as a researcher, to go into detail in different aspects of mathematical analysis. So I had to do the math. I had to go back into linear algebra. That's what MATLAB is really good at solving linear systems of equations. So that was something that I really had to relearn. But not only that, also learning about so-called mathematical morphology, so a special technique in image processing, about graph theory. All that was actually required, in particular, to bring and to increase the speed of TopoToolbox. And then finally, there was also the step towards getting dynamic. So that's, let's say, is what we are currently aiming for, to include more dynamic models into that environment. You will see a few examples just in a second. What I found particularly, let's say, challenging at the beginning, and perhaps you're with me here or not, was getting from here. So what you see, just a normal representation of a DM colored with some hill shading, to that. So which actually shows how much, or shows a depiction of flow accumulation, which shows how much water would flow everywhere if you had a particular input of water like all over the landscape. And unlike other image processing algorithms, that proved to be quite difficult to solve. Okay, because every pixel potentially depends on every other pixel. It's not just like a neighborhood operation where you can say, I want to calculate the slope, and the slope depends just on the 3 neighbors around each pixel. Or if you want to do an edge detection filter, that's actually not so difficult. In that case, potentially every pixel, of course it doesn't, but might depend on any other pixel. And so this brought me to this relatively simple equation, which is just a calculation of a steady state flow on a flow network, which is flow accumulation. I leave it with that. Later on, with TopoToolbox version 2, we tried to implement more techniques from graph theory on the one hand side, and on the other hand, we developed numerical objects. Okay, so what we adopted is to say, okay, a DEM is a grid, first of all. I mean, in the end, what is a DEM? It's a grid where each pixel value refers to an elevation value. But that's not all. Of course, your DEM has some geographic context. So you need to know where on Earth or on Mars or any other planet your DEM is actually located. So your matrix with elevation values also needs to be equipped with some georeferencing and so forth. And this is quite good to have that hidden somewhere in a numeric object. That's what grid object basically does. And well, just before, if you ran that command, DM equals grid object, and then you read your object, in that case a TIFF file, then you have that object in MATLAB. Okay, so based on this grid object, you can create a flow object. A flow object is the basis for a lot of topographic derivatives that somehow quantify fluxes of sediment, water, but that also allow you to delineate catchments. All that is required if you, or what you need for that is flow directions, and these are stored in a flow object. If you know GIS, and some of you said, or basically nearly everyone said, yes, I can work with GIS, at least at an intermediate level, then you probably have calculated flow accumulation, and what you had to derive is a flow direction grid. And well, that flow direction grid is basically in here, in that flow object. It's just a different way to store it, and by storing it differently, it's much faster. So just to give you a number of, if you run some commands in ArcGIS, for example, to calculate flow accumulation, an operation that would take a couple of hours in ArcGIS requires just a few seconds in TopoToolbox. Then, based on the flow object, you can derive a stream object. And what's that? Well, basically, it's a subgraph, a subnetwork of the flow object, which represents those parts of the landscape where you have constantly flowing water. So permanent water. It doesn't need to be defined like that, but it's like the easiest definition that based on the flow network, when a lot of flow paths flow together, then at some point you have permanent flow, and that could be a stream network, which is termed stream object in MATLAB or in TopoToolbox. So there are these 3 objects that somehow work together. You have a grid object, you derive flow directions, and based on the flow directions, you derive a stream network. But now these working with stream networks can also create new grid objects again. So for example, if you calculate, let's say, the catchments of each outlet of these stream networks, that would create a grid object again, which is a grid with drainage basins, basically. So these objects interact with each other, and that's how you can basically create workflows. And actually, you can create even more complicated workflows by adding new objects that I've mentioned just before. Divide object, for example, which deals with divide networks. PPS, which is a point pattern on stream networks object. We won't deal with that this time. We did that last time. Or for example, if you want to create swath objects or swath, this is something that can also be done. So I said before, one important part of TopoToolbox and its current development is to get more and more dynamic. I said that some operations can be done very quickly on the way or using the way that we implemented some of these topographic derivatives like flow directions. And so there is a landscape evolution model, which actually works, if you want, which is quite easy in the end to do once you have all these functions. So this landscape evolution model is just a compilation of the existing functions, let's say. And just to give you an example, now I've shown this here because this is the eye of the Sahara, and it just shows the topographic expression of a dome uplift. Okay, and since it's very dry in the Sahara, it's nicely depicted here so that you see these different structures and rock layers basically being cut at the surface. Now you can do something like this in a similar way now. Of course, not exactly like that, but this is the newest stuff that we did in TopoToolbox. It's a TTLEM 3D. It's a 3D model, and which then allows you to have, you see how the different layers basically come out at the surface because of domal uplift and create these funny patterns, thus simulating landscape evolution with a layered stratigraphy. So this is probably interesting for those of you who work in a tectonic, let's say, context, tectonic geomorphology. But of course, it's also interesting to work with TopoToolbox when you are working in a hydrological context. So just to give you some examples, we have you can do a lot of pre-processing of DEMs for hydrodynamic models. We did that for modeling outburst floods and landslide lake outburst floods, just to make sure that a DEM that you obtain from a global DEM, like a 30-meter DEM, is processed in a way that it can be digested by some hydrodynamic modeling environments like HECRAS or so. So different kinds of stuff that we did here in the field of hydrology. As I said before, some of the newest stuff that we have been developing is graph flood, which allows you to calculate, let's say, using the St. Valence equations without no momentum, but calculate the extent of water. And so what you see here is basically a depiction of flood extent by precipitation rate. So the different colors here basically give you an idea what the flood extent would be for a certain precipitation rate. So you get much more realistic flow patterns using this approach than just the simple approaches that are commonly used in GIS. And then, of course, in geomorphology, we can do a lot of stuff like analysis of river profiles, which we do to understand the landscape's erosional history and its controls, analysis of divide dynamics, landslide susceptibility analysis, flood wave propagation and sediment dynamics. So for example, the study that we did on a Chamoli event, Chamoli disaster, which was also published in Science, was also partly done in TopoToolbox. And what I'm actually using it for is also for the long-term simulation of landscape evolution for the planning of nuclear waste repositories. So I'm working together with the Swiss agency for the disposal of radioactive waste. This requires to have an idea about how the landscape evolves over the next million years. And that's where suddenly the stuff that I developed before, just in having in mind some academic ideas, got some practical value. Okay, and some new stuff that we are going to implement is, as I said before, some dynamic models. This is, for example, a model from Stefan Hergarten, a modified Wellme model that allows you to model rock avalanches. And how that would look like is, like in this little video, this is what it shows is the Eiger North Face, one of the major north faces in the Swiss Alps. And now if you would have a big chunk of rock that would detach from that north face, you would probably have something like this, okay? Where the colors depict the height of the flow, and the velocity is then, or the friction is a function of the velocity to the square. And basically doing simulations with that one gives you quite realistic patterns, both of the run-out length as well as the depositional patterns of these rock avalanches. So it takes apparently 165 seconds for such a landslide to evolve from this about 2,000 meter drop that occurs here. Okay, I think we leave it at that point. It's 5:45. We then have a few minutes to take a rest. You have also some time for tomorrow. If you had some problems installing the software, then just do it. And then tomorrow we can just start right away with developing the code to reach that aim. Okay, let's model erosion rates from topographic data. Okay? See you tomorrow. Yes, there's a question.
Hi. So my question is that can we do orthorectification of terrestrial images using the toolbox or not?
No, I wouldn't use that for this. So there are some basic ways to reproject your data, to do grace value interpolation, and so forth. There are ways to do that in MATLAB. So the image processing toolbox offers a lot of ways to georectify imagery, but that would be a completely different topic then. Yeah. But you can do that.
Using this toolbox, we
not the TopoToolbox, but use the image processing toolbox in MATLAB.
So mainly this. So I have to do terrestrial mapping. So orthorectification is not possible if I have some GCP points and interpolation.
Well, it's not what TopoToolbox is used for, but you can use, of course. Let me show you. Doc.im register. This is an image processing function. I know that's for something else, but it does image registration. And so if you have some control points, it would work the same. So there are some functions, let me see. imrecconfig, imreccore, so there are a lot of functions to do that. Okay.
Thank you.
Okay, see you tomorrow.